This is Dr. Carolyn Scarla. In this series of videos, I will perform two experiments. The objective of the experiments is to illustrate the manual data acquisition process. You will collect raw data, set up a spreadsheet, perform calculations, plot the data, calculate trend lines, assess the goodness of fit of that trend line to the experimental data, and assess the experimental error between your measurements and the values provided by the manufacturer. This is part one of the three-part video series. This is the outline for the series of DAQ Lab videos. Our intent on performing experiments related to mechanical engineering and electrical engineering is to illustrate that DAQ, or experimental data acquisition, and data analysis methods are similar no matter what type of experiment is being performed. In part one, the first experiment, the mechanical engineering experiment, you will collect and analyze data with the objective of measuring the spring constant of a simple extension spring. First, I will cover an introduction to springs. Following that is a description of the materials required to perform the experiment, the experimental apparatus and method, and the collection of raw data. Finally, I'll perform the actual experiment while you collect your own set of raw data from the images that I'll provide. In the part two video, the second experiment, the electrical engineering experiment, you will collect and analyze data with the objective of measuring the nominal resistance and sensitivity of a thermistor. In the part two video, I will cover an introduction to thermistors. Following that is a description of the materials required to perform the experiment, the experimental apparatus and method, and the collection of raw data. Finally, I'll perform the actual experiment while you collect the raw data from the images that I'll provide. In the part 3 video, I will lead you through the process of taking your raw, manually written data through generating a spreadsheet with required calculations to get to the required variables, generating a plot of the data, and using Excel's trendline capabilities. You will assess the goodness of fit of the trend line to your experimental data and calculate the experimental error between your measurements and the manufacturer-provided data. Experiment 1. First, an introduction to springs. Springs are devices used to store mechanical energy. There are different types of springs. Extension springs are formed with a coil of wire that is loaded in tension. As the force exerted on the spring increases, the spring's length increases. Compression springs, also made with a coil of wire, are loaded in compression. As compression force exerted on the spring increases, the spring's length decreases. Flat springs, such as leaf springs in the suspension of vehicles, are made from a flat piece of spring steel. Torsional springs, also made from a coil of wire, are loaded so that the coil is twisted about the longitudinal axis of the coil. The governing equation for springs is given here and is illustrated by the free body diagram shown. Notice that the downward force F is equal to the upward force K times X. This illustrates the need for the negative sign in the equation. The negative sign indicates that the force exerted by the spring is equal and opposite in direction and magnitude to the force that has been applied to the spring. Now let's look at the definition of each of the variables in the equation. The variable F is the force that is applied to the spring. The variable X is the change in length from the unloaded length of the spring. The variable K is the spring constant. This is the unknown that you will determine in this experiment. The spring resists the force that is applied to it. One important item of note with this experiment is that you will be measuring the mass of a bucket and rocks that will be suspended from the lower end of the spring. And mass is not force. You will have to perform a calculation on your raw data to determine the value of force that was applied to the spring in each step of the experiment. Well, that one is easy in SI units. Force is equal to the mass times gravitational acceleration, which is 9.8 meters per second squared. In English units, gravitational acceleration is 32.17 feet per second squared. To make things even more confusing, in the English system of units, the unit of mass is actually called the slug. Now, I hate slugs both in my garden and in my spreadsheet, so for the sake of this experiment, we will refer to 1 pound force as the force of gravity exerted on 1 pound mass. The unit symbol for pounds force is lb sub F, and the unit symbol for pounds mass is lb sub M. This is an example of a data sheet for a spring purchased from the vendor, McMaster Carr. It contains important information about the spring that is manufactured from music wire steel. Note that the unit lbs on this data sheet refers to pounds force. The spring type indicates that this is an extension spring. The length of the unloaded and unextended spring is 2 inches. The outer diameter, or OD, of the coil of wire is 0.5 inch. The diameter of the wire is 0.045 inches. These three numbers define the spring as you see in the text just above the image of the spring. The extended length of the spring at the maximum load is 4.61 inches. The minimum load is 0.7 pounds. Note the arrow and highlighted text at the bottom of the page. The minimum load is the amount of force required to start to extend the spring. This means that if, for example, the spring is loaded with 0.5 pounds force, the spring will remain at its unloaded and unextended length. This means that the spring will behave in a non-linear manner. By that, I mean that the value of the spring constant is 0 pounds per inch for any load less than the minimum load. The maximum load is 7.5 pounds force. Note the arrow and highlighted text at the bottom of the page. The maximum load is the amount of force required to fully extend the spring without permanently damaging the spring. If the spring is loaded with anything greater than 7.5 pounds, the spring will experience some permanent deformation and will be unable to return to its unextended length of 2 inches. For that reason, we will be using a safety factor of 1.5. This means that the maximum load that will be applied to the spring will be around 5 pounds force. Finally, the rate on this sheet is what I refer to as the spring constant. This is the slope of the force versus extension curve between the minimum and maximum loads. In this experiment, this is the value that you will be determining for the spring. Now let's look at the experimental setup for experiment 1. To conduct this experiment, the required materials include a test stand, a clamp that attaches to the test stand, a ruler, a bucket, an S-hook for hanging the bucket from the spring, a digital scale, a bucket of river rocks, a scoop, tape, and the test specimen, the spring. You will need to provide a piece of paper and a pen or pencil so that you may collect the data from the experiment. The test apparatus is shown in the photo on this slide. The end of the clamp with the green fingers was unscrewed from the part that attaches to the stand. The spring was slipped onto the threaded component of the clamp, and the clamp was reassembled. The ruler was taped to the clamp such that the metric side of the ruler was placed close to and parallel to the spring. The ruler will be used to measure the position of the upper and lower ends of the spring's wire coil. In order to make it easier for you to select a point of reference at the upper and lower ends of the coil, I used a marker to place a black mark on the first coil at the top and the bottom of the spring. The S-hook was used to suspend the bucket from the spring. The scale that you're going to be using in this experiment is quite easy to operate. The button on the left is the on-off switch. When the scale is turned on, if the scale does not read 0, the 0 tare button just to the left of the display screen is pressed to 0 the scale's reading. The button to the right of the display screen switches the scale display from SI to English units. Notice the very small G just to the left of the 0 at the top of the display. This means that the scale is set to measure grams and kilograms, that is, SI units. If the kilogram pound button is pressed, the G will change to ounces. This means that the scale is set, in this case, to measure pounds and ounces, that is, English units. For this experiment, measurement of mass will be made in SI units. The first masses to be suspended from the spring are the bucket and the S-hook. They must be placed on the scale to measure their mass before the experiment begins. After that, river rocks will be measured on the scale for each incremental mass that will be added to the bucket. They will be measured in the blue plastic scoop. Therefore, the scoop is placed on the scale and the 0 tare button is pressed. That means that the mass of the rocks to be added to the bucket will be measured without adding the mass of the scoop to the mass of the rocks. The experimental method includes the following steps. The readings from the ruler are recorded for the positions of the top and bottom of the unloaded spring's coil. You will select spots on the spring that you will use as your reference points throughout the experiment. The first incremental mass is the sum of the masses of the S-hook and the bucket. After the bucket and S-hook are suspended from the spring, the readings from the ruler are recorded for the positions of the top and bottom of the unloaded spring's coil. Before the first incremental mass of river rocks are weighed, the scoop is placed on the scale and the scale is tared so that the scoop's mass is not measured. Rocks of approximately 50 grams will be added to the scoop and the incremental mass will be measured and recorded. That mass will then be added to the mass of the bucket and the S-hook and recorded in the cumulative mass column of your data sheet. The rocks are added to the bucket and the readings from the ruler are recorded for the positions of the top and bottom of the unloaded springs coil. Each successive incremental mass of approximately 50 grams will be recorded. The cumulative mass will be calculated. The rocks will be added to the bucket, and the readings from the ruler for the positions of the top and bottom of the spring will be recorded. This process will be repeated until the spring has been extended by approximately 1 inch, or the bucket becomes full of rocks, or the bucket and the rocks combined weigh 5 pounds, whichever comes first. Before you begin the data collection, you will need to set up a data collection sheet with 4 columns. The first column will contain, excuse me, repeating. The first column will contain the incremental mass that is added to the bucket. The second column contains the cumulative mass suspended from the spring. The third column is for the reading from the ruler for the position of the top of the spring coil. And the fourth column is for the reading from the ruler for the position of the bottom of the spring. Your form may be computer generated or completely handwritten. I have provided a copy of my blank form here as an example. Following is the experiment. To review, I drew a black mark on the top and bottom coil of the spring. This image is of the unloaded spring. I want you to notice something in this image. The numbers are increasing in value from the top to the bottom of the spring. Keep that in mind, please, when you are recording your measurements using the ruler. In the close-ups that will appear next, please note that I have cropped them so that you will see 2 numbers. Those numbers represent centimeters. This is intentional so that you will record the ruler measurements correctly. This is a close-up image from the photograph at left. It shows the top of the spring and the ruler. On the ruler, the 7 and the 8 refer to centimeters, and the individual hash marks are millimeters. Select a landmark on the top coil of the spring. You may want to hold a piece of paper or a ruler up to the computer screen in order to help you determine your measurement. In this image, based on my selected landmark, I will record a number that is slightly less than 80 millimeters or 8 centimeters. The video will pause for you to take your measurement and record it on your raw data sheet. Click on the Resume button when you are ready to continue. This image is a close-up from the photograph at left. It shows the bottom of the spring and the ruler. On the ruler, the 11 and 12 refer to centimeters, and the individual hash marks are millimeters. In this image, based on my selected landmark, I will record a number that is somewhere between 10 and 11 centimeters, or between 100 and 110 millimeters. The video will pause for you to take your measurement and record it on your data sheet. Click on the Resume button when you are ready to continue. The left and center images on this slide show the masses of the bucket and the S-hook. The right image shows the S-hook and bucket after they are hung from the spring. Sum these 2 masses and record the value as the first incremental mass. Please note that the mass is in grams. You will also record this as your cumulative mass because this is the first mass that is being added to the spring. The image shown is a close-up of the spring after the first load was hung from the spring's bottom loop. The image at top right is a close-up of this first image. On the left, make your measurement, record it, and then click on the Continue button. The image at bottom right is a close-up of the image at left. Make your measurement, record it on your sheet, and click Continue. At this point, I'm ready to start adding river rocks to the bucket. First, I placed the empty scoop on the scale and pressed the 0 tare button. This then sets the scale to 0 with the scoop resting on it. After taring the scale with the scoop on it, I will be able to measure the mass of the river rocks without having to subtract the mass of the scoop each time. Then I chose to make the incremental masses of rocks to be approximately 50 grams for each reading. The first set of river rocks were measured, as you can see in this image, at 48 grams. Record that incremental mass in the first column and add that to the mass of the S-hook and the bucket to get the cumulative mass for load 2. Once the rocks were measured on the scale, they were transferred from the scoop to the bucket. The image shown is a close-up of the spring after the first load was hung from the spring's bottom loop. The image at top right is a close-up of the left image. Record your measurement and click on the Continue button. The image at bottom right is a close-up of the left image. Record your measurement and click to continue. I'm not going to provide very much more commentary for the remainder of the experiment. The experimental procedure is going to be a repeat of the application of load 2. Have you noticed on this slide that some of the red background is showing between the spring's coils? This extension spring is finally beginning to visibly show extension. This is the conclusion of Experiment 1.